Now we want to move on and look at some fundamental notions when we're talking about vector spaces. And the three main ones are the notion of a subspace, the span of a collection of vectors, and linearly independent set of vectors. So first we're going to define a subspace, and we're going to say that given any vector space V, W is a subspace of V, if and only if W is a non-empty subset of V. And one way that we can show that W is a non-empty subset of V is the fact that the zero vector always has to be in W. So if you can show that, then you've shown it's non-empty. And also, W is closed under addition and scalar multiplication. Another way of saying this is to say that W is closed under linear combinations. What that means is, it means that if U is an element of W, then any scalar times U is also in W. And given two vectors, U, V, and W, their sum has to be in W. That's what this sort of closure means. It means that things in the set stay in the set under addition and scalar multiplication. Okay, so a really simple example that we're going to come back to, which is important, is the kernel of a matrix. So we said given an m by n real matrix A, the kernel of A is a subspace of Rn. I'm going to claim that, I haven't shown it. And we recall before we get into the details of showing this that the kernel of A is defined as a set of all vectors in Rn such that Ax is equal to 0, the zero vector. Okay, and we're going to show that this is a subspace of Rn. Well, first of all, we note that by definition it's a subset of Rn because we're saying that all the vectors have to come from Rn, and we know that it's non-empty because we showed that the zero vector is always in the kernel. And we can show that the kernel of A is closed under linear combinations, and here's what you have to show. And I would suggest that you show that. Okay? And so this is going to be a subspace of Rn. We're going to use this fact a great deal. Okay, we're also going to introduce a little bit of notation. So if we have, say, some vector space capital V, and we have m vectors, v1 through vm, what we're going to do is we're going to not think of them so much as a set. We're going to think of them more as an ordered list. Okay, and we're going to find that in proofs, this is actually a very useful way of working with collections of vectors. And so we're going to write some list L as being an ordered m tuple of those m vectors. And some people call this an ordered set. Okay, it's just a finite sequence. One thing I want to emphasize, though, is that we want to think of a ordered list, like I said, more like a finite sequence of vectors than a vector of vectors. It's possible to interpret this L as being a vector where the components are vectors. We don't want to think of it that way. And the reason why is we're going to want to manipulate this list. We're going to want to add or remove things to that list, okay? So if we think of it as a vectors or vectors, we usually think of the number of components in a vector as being fixed, right? And we wouldn't do that. But if we think of it as a list that's ordered, we can always add things to the list or take things out of the list. Okay? All right. So the first thing we want to talk about is the span. And in order to do that, we have to first define what a linear combination of a collection of vectors is. So if we have some vector space V and some ordered list capital U, we're going to say that V is a linear combination of the vectors in U if it can be written in the following form. It's basically a weighted sum of the vectors in capital U where the weights are real numbers. Okay? Now, we're going to define the span of a list of vectors as the collection of all linear combinations of the vectors in that list. Okay, so notice this V is just one linear combination of the vectors in capital U. But if we look at the set of all linear combinations of the vectors in capital U, that's what we call the span of U. So again, if we write capital U as follows, then the span is basically all of the vectors in capital V that can be written as a linear combination of the vectors in U. Okay? And so in a sense, this kind of, we think of the span of U as all the vectors we can possibly write as linear combinations of U. Okay? Notice that the span of U is, a collection of vectors. It's not just the vectors in U anymore. There's an infinite number of vectors in the span of U. Okay. Two important things about the span. First of all, you should convince yourself that the span of U is a subspace of V. In other words, we should show that the span of U is a non-empty set and it's closed under addition and scalar multiplication. And that's not hard to do, but you should definitely prove that. And one term that's kind of appropriate to bring up now is a finite dimensional vector space. Okay, and what we're going to say is if we have any vector space V and there's a finite list whose span is equal to V, then V is said to be a finite dimensional vector space. And what that means is it means that any vector in capital V can be written as a linear combination of a finite number of vectors. Okay? We haven't defined what dimension is. Okay? We're going to. But this is the definition of a finite dimensional vector space. And we'll get to what dimension means later on. Okay, so some of the times we want to show that a given set of vectors spans a given subspace. So let's just take an example where we have two vectors, U and V, in the vector space capital V, and S is some subspace of V. And we want to show that the span of UV is equal to S. Okay, notice that this is a set. So if we want to show two sets are equal, first we have to show that every linear combination of U and V is in S. In other words, every element in the span is in S. But then we have to show that every vector in V is in the span of UV, which means it can be written as a linear combination of U and V. So as some examples, we can show that the span of these two vectors is actually in R2 is actually this set. Our capital S is all the scalar multiples of the vector 1, 1. Okay, and we can show that. We can show that everything here can be written in this form, and everything in this form can be written as a linear combination of these two vectors. Okay. We can show that the span of these two vectors is R2. In other words, every vector in R2 can be written as a linear combination of these two vectors, and every linear combination of these two vectors is an element of R2. Notice that the same vector space can be spanned by a different set of vectors. You can also show that the span of these two vectors is R2. Okay? In the same sort of way, of course. Now, a very important concept is the concept of linear independence. So, for example, we may have a bunch of vectors spanning a vector space, but some of them may not be necessary. And so linear independence is a really important condition. It's going to tell us whether every vector in that list is important or necessary. So let's define linearly independent. We're going to say that if we have some ordered list of vectors, then they're linearly independent if and only if the only way we can have a linear combination of those vectors giving the zero vector is if all the coefficients are zero. Okay? Very important definition. And the import of this definition is that the only linear combination of the vectors in capital U that give the zero vectors is the trivial linear combination. In other words, all the coefficients in the linear combination have to be equal to 0. This is the only linear combination that gives 0. Okay. Now, you can prove two things that are really important. The first you can prove is that if U is a linearly independent list of vectors, no vector in U can be written as a linear combination of the others. So, for example, if you look at capital U, it consists of m vectors, right? An ordered list of m vectors. What we're saying is that this list is linearly independent if and only if no vector in this list can be written as a linear combination of the others. And this isn't hard to prove, but you should prove this. The second corollary is that a single vector is linearly independent as long as it is not the zero vector. Notice that this list here, okay, is a list of any m vectors where m is a natural number. So it makes sense, although we don't normally do this, it makes sense to talk about one vector being linearly independent. And formally, to do this proof, we have to use a result about vector spaces, which we didn't prove, but it follows as a consequence of the definition of vector space, which is that if a scalar times a vector is the zero vector, then either the scalar has to be 0 or the vector has to be the zero vector. So using this fact and the definition of linearly independent, we can prove that a single vector is linearly independent as long as it's not the zero vector. Okay, now if you're not linearly independent, you're linearly dependent. And this is just an important concept. And so we're going to define linearly dependent. We're going to sometimes use the abbreviation LD, just like we used LI for linearly independent. So we're going to say, okay, given a collection of vectors whose ordered list we express as U, they're said to be linearly dependent if and only if there is a linear combination of the vectors giving the zero vector that does not require all the coefficients to be 0. Okay? So there is some non-trivial linear combination of the vectors in capital U that will give the zero vector. And if you look at this, you'll see that it is the negation of linearly independent. Okay, these two are the opposite. A list of vectors is either linearly dependent or linearly independent. There's no other possibilities. Okay, corollaries that you should prove. First, you should prove that if we have a non-empty list of vectors U, it's linearly dependent if and only if one vector in that list can be written as a combination of the other vectors in that list. And if you think about it, this is the negation of the previous theorem or corollary we proved for linearly independent vectors. The second corollary that's useful is that any ordered list with the zero vector must be linearly dependent. And again, that's easy to prove, but you should convince yourself that you can prove that. Okay, now we're going to come across some really important theorems about linear independence. The first theorem says the following. It says that if I have some ordered list of linearly independent vectors, then every vector in the span of U can be written as a linear combination of the vectors in capital U in only one way. Okay, that's a very important result. And we're going to prove this. It's such an important result. So we're going to use contradiction. So let's say, okay, suppose we have a list of vectors that's linearly independent, but guess what? I have two ways of writing them as linear combination of the vectors in U that are different. Okay, so we're going to suppose that capital U is a linearly independent set, but there's a vector in the span of U that can be written two different ways. Okay, and so let's look at what that would imply. This would imply that there'd be one linear combination that would give me this vector U, another linear combination of the vectors in capital U giving me U, but not all of the coefficients are equal for corresponding vectors in capital U. Okay, so these are different linear combinations. And let's show why that gives a contradiction. Because notice when I subtract these two expressions, I get the zero vector. Okay, and notice that not all of these coefficient differences are zero. So notice what I have now is I have a non-trivial linear combination of the vectors in U that gives me the zero vector. But that can't happen because the vectors are linearly independent. This would suggest that they're linearly dependent. Because remember, to show linearly dependent, all I have to do is come up with one linear combination of the vectors where the coefficients are not all zero that give the zero vector. And I've come up with one here. So therefore U is linearly dependent, but that contradicts the fact that U is actually linearly independent. There's our contradiction. Okay, we're going to go on next and talk about basis vectors.